So just a reminder that the information about homeworks and so on is on the web page. I don't have to keep telling you that there will be homework assignments, so you need to check this periodically. There's a homework due today, which I see has appeared, and there's another homework assigned due in 2 weeks. Does anybody have any questions? Yes.
The homework today had LabVIEW components.
Yeah.
You want us to turn that in on bSpace?
You can turn them in on bSpace. If you turned in a printout that is sufficiently well documented, that's enough. But if not, please do turn them in on bSpace. Okay. Okay, then email them to the to Di or to Kevin. Actually, to Kevin would be the better choice because he's coordinating with the reader. Okay. Anything else? All right. So we left off last time looking at this thought experiment due to Ross Bodick. So the idea was we were talking about sensors and actuators. And we were talking about this idea of being able to take an iPhone and enhancing, compensating for its small screen by allowing you to pan over the page that you're looking at. So the question is, if you were to attempt to do this, what kind of sensors would you use and how well would they work? So where we left it off last time, you guys were going to think about it, and we were going to have a discussion here. So let's have a discussion. So what are your thoughts?
Combination of the accelerometer.
So a combination of the accelerometer and the camera. That's a pretty good idea. What would happen if you just used the accelerometer by itself without using the camera? Yeah.
You have to integrate the accelerometer values, and you probably have such a huge error.
Yeah, that's actually a very good point. So accelerometer measures acceleration, and what we really want is position, not acceleration. And position is a double integral of acceleration, and you're going to get accumulating errors, right? So presumably, if you have a small error in the measurement of the acceleration, this thing will drift, right? So it'd be kind of annoying. You'd be looking at a page, and it would be sort of wandering to one side and a little bit around just as errors accumulated. So that would be a problem, right? This fact that really what we want to measure is position, not acceleration. What else? What other problems could you run into using an accelerometer? Yeah. Yeah, if you're in a plane or a car and it's moving around, so envision yourself sitting at the BART station. Your BART train is still, you're reading your newspaper. The BART train pulls out of the station, your newspaper slides out from under you. It would be very disturbing, right? So that would be a problem. What else? What other problems could you run into using an accelerometer? Yeah. Sorry? That's right. You got to make sure you're on the right plane. I mean, accelerometer is very good at measuring tilt, right? And it actually has a lot of trouble telling the difference between tilt and acceleration. So the issue is that if you tilt it this way, it could misinterpret that as panning very easily, right? Yeah. Yeah, so perhaps you could take advantage of this. In fact, one could think of a design where instead of moving to one side to move your view of the page, you just tilt slightly and you look at that part of the page, you look at that part of the page. That actually might work better because accelerometers are very sensitive to tilt because what they're really measuring, remember, so I showed you a picture last time of a silicon accelerometer which has silicon substrate with some ridges and then suspended silicon fingers. And when you accelerate in one direction, the spacing between these changes, right? But also when you tilt, right? If you hold the thing up vertically like this, the suspended fingers will be pulled down by gravity with a fairly substantial force compared to what you get from acceleration, right? A force of 1g, approximately 10 meters per second squared. That's a pretty substantial force, and it takes a lot of acceleration to match 1g. So it's really a lot more sensitive to tilt than it is to acceleration in sort of the straightforward way. And in fact, when you're using it in the iPhone, it tends to be used more for measuring tilt than for measuring acceleration. In the Nintendo Wiimote, it's actually used for measuring acceleration. The Wiimote has an interesting trick, which is that they do combine it with a camera. So you put above your TV set a bar which has infrared beacons in it. So it's actually doing infrared illumination. And there's a camera in the Wiimote, an infrared camera, that spots these beacons. And that tells the system the position of the handheld relative to the screen. So the way that it tells that you're pointed at the screen is not using the accelerometer. Okay? In fact, it's generally telling position by looking position. Well, it's combining the two pieces of data, but in any case, it tells the orientation of the Wiimote relative to the screen using the infrared camera more than the accelerometer. Okay. So the idea of using the camera on this thing is kind of interesting because if you assume that the backdrop behind you is fairly fixed, right, then you could be able to tell when the thing is being panned by looking at the image, right? But once again, you would have trouble distinguishing tilt versus pan. Right? So that it'd be a pretty challenging design using the sensor data that we've got. One of the key points here is that measuring the location of an object is quite difficult. The problem is called localization. Okay? And those of you who have grown up in the era of GPS think it's easy. Trust me, it's not. GPS is kind of an amazing system that when you can make it work for you, that's great. There are situations in which it doesn't work very well indoors, or if you're trying to measure precision on position on very small scales, it doesn't work very well either. And measuring position is pretty challenging. There's a few other kinds of measurements that we can make. Here is a strain gauge. So this is an interesting one. I don't know, 3 or 4 years ago, one of the professors here, David Culler, got a lot of press for instrumenting the Golden Gate Bridge with a whole bunch of sensors. These included accelerometers that were measuring the sway of the bridge in the wind. Okay, they had the advantage there that they could really fairly precisely control tilt. So it could, an accelerometer could be used reasonably accurately to measure the sway of the bridge. But they also put in strain gauges, and strain gauges are really very simple devices. You just use a stretchable material that when it stretches, it gets narrower and its resistance increases, electrical resistance. So you just measure the electrical resistance of this thing, and so as it stretches, the resistance goes up. So you can use that to measure even very, very slowly changing stresses. So geophysicists use this, for example, to try to predict earthquakes. They put in strain gauges in places strategically placed along a fault to try to detect very small movements in the fault and use them to measure increases in the strain on the rocks below. So there's a number of issues. One of the things that is really important is understanding your sensors and being able to construct models of your sensors. You need to understand what they're measuring. It's not enough to just say, well, okay, it's a thermometer, it measures temperature. It's never that simple. Okay? You have to kind of understand exactly how the measurement is being done, what is being measured, what is not being measured, how noisy is the data that you're getting, How well calibrated is the sensor? Are you getting absolute information or only differential information? These kinds of questions are essential. So one of the key things that you stumble against almost immediately with using sensors in a embedded systems context is that you want to sample the data. And as you all know from EECS-20 or something equivalent, when you sample data, you run the risk of misinterpreting the data because of aliasing. So here is a sinusoidal stimulus being sampled at a rather low rate. And it appears, if you just look at the samples, the red samples, it appears to be a sinusoidal stimulus, but of an entirely different frequency than the original one. So we talked about this last time when we talked about the Kingvale blower controller for the snowplow, right? That the way that they worked this was they put magnets in the road, and they used a magnetometer underneath the vehicle to measure their lateral position on the road. And you have to take into account that if the curvature of the road is actually following the blue line, but your magnets are placed at distances corresponding to the red samples, then you could drastically misinterpret the curvature of the road. Okay? So these are the kinds of things that you have to take into account when you design these systems. Aliasing also arises in multidimensional sensors, such as image sensors. This is an image sensor where the finite precision of the pixels produces these so-called moire patterns. So these patterns that you see of this sort of bug-shaped phenomenon here, those are artifacts of the sampling. Those are not properties of the original image. And similarly, these stripes that you see are artifacts of the image. This image is actually just horizontal stripes slightly tilted. Okay? There's no vertical stripes in this at all. It's just horizontal stripes slightly tilted and being sampled. So aliasing is an issue. Conditioning for noise is an issue. And there's quite a bit of detail in one of the chapters of the textbook on conditioning for noise. But the intuition that you need to keep in mind is really pretty simple, which is that if you have a good model of the data that you're trying to measure, what are you trying to measure, right? You can identify properties of that and then make use of those properties to eliminate noise. So if you know that the data that you're trying to measure lies within some frequency band. So for example, if you're trying to measure a human tilting an iPhone, you know that it's a pretty low frequency thing. How fast can a human tilt an iPhone meaningfully in the way that they're responding to, I mean, they're controlling a user interface? Well, you know, it's down on the order of a hertz kind of thing. So if you're measuring data that has frequency content higher than a hertz, you can filter that out safely, and you eliminate a huge amount of the noise power. Okay, so the picture here is illustrative of this. Suppose that the signal that you're trying to measure has frequencies ranging over some narrow band. That's the bandwidth here. Okay, so that's what you want to measure. The noise has frequencies ranging over a much wider band. If you bandpass filter this using a filter that looks only at the band of interest, then you drastically reduce the noise power. The noise power is proportional to the area under this curve. Okay? So the signal power is the area under the blue curve. The noise power is the area under the red curve. The signal to noise ratio is the ratio between those two powers. Okay? The ratio between those two powers of the filtered signal is much better than the ratio of the two powers with the unfiltered signal. That's the principle of a whole bunch of math that is given to you in towards the end of, what is it? I forget which chapter. One of the chapters in the book. Okay? This is all based on Parseval's relation, by the way, if you're familiar with that. Now, I've talked mostly about sensors, but actuators are also a fairly critical issue. Does anybody here know how a pulse width modulator works for controlling a motor? Yeah. You want to give us a short synopsis? What's your name, by the way?
Ryan.
Ryan.
So a pulse width modulator, so the principle is
Yeah. So let's understand why this works. Let me just do a little sketch here. If I can do, let me get this on full screen. Is that showing? So if I give a motor a stimulus that, as a function of time, is a voltage that looks like this. Okay? What's the motor going to do? Well, it depends a lot on what the time scale is here, right? If the time scale is rather long, the motor is presumably going to start and then stop, and then start and then stop. However, if the time scale is very short here, the motor has a lot of inertia, right? So you give it a little boost while your voltage is high. You stop giving it boost while your voltage is low, but it keeps going anyway because of Newton's second law. So you give it another little boost, and you stop giving it a boost, and you give it another little boost. And if you turn it off on and off fast enough, just because of the inertia of the motor actually acts like a low-pass filter. It's going to turn at a pretty steady rate, as long as you do this, turn it on and off fast enough, right? So as a consequence, you can control a motor very simply. If you want it to go faster, just give it a longer boost each time. Okay? And the motor will turn faster. If you give it a shorter boost each time, it'll turn slower. This is called pulse width modulation. Why do we do that instead of just giving it a voltage that, if we want it to go fast, we give it a high voltage. If we want it to go slow, we give it a low voltage. Would that work, by the way, for a motor? Sometimes?
I mean, you have to overcome the inertia of the motor, so you want to get like low.
That's true. I mean, in motors, actually, their response to voltage is not linear. In particular, if they're still, you have to overcome a static friction to get them going in the first place, right? So it's not a completely linear response. So that's one issue. But let's suppose that you're in a linear operating mode. So the motor is already turning, and its behavior is approximately linear. Then you can, in fact, control the speed of the motor by controlling the voltage that you deliver. Why would it be better to do pulse width modulation instead of controlling the voltage? Yeah.
one, it's easy to do with the digital controller.
Right.
It's two states, and digital controller seems to be time to up.
Yeah.
And it's also more efficient.
Is it more efficient?
I think it is, because you have higher voltage.
Huh. I honestly don't know about the efficiency, but yeah, you.
I'm not sure about the efficiency, but I'd say it's also bad because
Right. Yeah, that's a major problem. I mean, first of all, one of the issues is that with motors, I mean, if it's a big motor, you've got to deliver a substantial amount of power to it, right? So the circuits have to be able to handle, a lot of power, which means either high voltages or high currents or both, right? And designing circuits that can handle high power over a whole range of voltages is much more difficult than designing circuits that can handle high power at only a single voltage, right? A single power transistor connected to a power supply can deliver an enormous amount of power, right? But it's either on or it's off. And when it's on, it's delivering a lot of power. When it's off, it's not delivering any. And that's a much simpler circuit than an amplifier that has to maintain linearity and deliver a lot of power. Okay? So linear power amplifiers are very expensive devices compared to the circuit that you need to deliver power through an on-off schema. Okay? Other questions, comments?
Do you know
Yeah.
the actual expense of one of those linear power amplifiers?
Well, so the question is, do I know the actual expense of a linear power amplifier? A good rule of thumb is that an audio amplifier that drives your speakers is a pretty good indication, right? You know, what does it cost to get an amplifier that'll deliver 100 watts to an 8 ohm load? Okay, about $100, right? And that's a mass-produced consumer product. How much does it cost to deliver 100 watts to an 8 ohm load using this scheme? Probably a penny in mass-produced, I would guess. You know, I mean, it's a single transistor, right? Well, no, you need the power supply, so it's more than a penny, maybe $1. Okay, it's a big difference in the cost of these devices. So pulse width modulators are you know, when you can use them, they're really a very good way to drive motor controllers. Now, getting precision out of them requires pretty detailed modeling of what the motor does, how the motor behaves, and you know, if your models are incorrect, you will get unexpected behaviors. You would like to be able to design motor controllers to be very precise. Here's a pretty nice example here of a prosthetic hand that has the ability to apply very sensitive forces. So they advertise that it can lift a paper cup without crushing it. That is a big deal for a prosthetic hand, right? And it's absolutely non-trivial to do. That requires very precise control over these motors. At the time that I looked, which was about 4 years ago, this particular bionic hand sold for $18,500. So not a cheap device and not easy to control. Cameras. Cameras are a pretty flexible sensor. They can detect things over a pretty wide range of stimuli. You can use cameras to look at you know, physical images. You can look at infrared. You can look for beacons. You can look for reflectors. I mentioned that localization is a challenging problem. There's some pretty fancy localization systems that are out there. In fact, many modern movies are made using these. So one of the more elaborate ones is made by a company called PhaseSpace, and we have a setup, a PhaseSpace setup over in the Hearst Mining Building. And the way that it works is that you put on a bunch of beacons on your body. You're typically wearing a bodysuit. You just put on a jacket that has these beacons attached to it. And these beacons are LEDs that emit a regular pattern so that the sensor can actually distinguish between the beacons. And then there's a whole bunch of sensors scattered around the room that do triangulation on the position of these beacons so that they can tell, you know, where each of the beacons is. So this particular system is used in movie making. They set up movie sets where, you know, the actors will go, you know, charging up the ramp and, you know, fighting sword battles and so on, wearing their, you know, jeans and T-shirt or whatever they wear. And then a computer will synthesize, you know, 10-foot tall, blue-skinned creatures, you know, running through the woods and climbing trees and so on, right? That's how they do it, okay? They get the very realistic motion from the actors, and the actors can be very expressive. They even put these sensors on various points on the faces so that they can get facial expressions to very high precision, rendered then into some creature that is very different from the visual image. So we have a setup that we're going to be putting in the lab that is similar to this, but is a little bit simpler. It uses reflectors, infrared reflectors, and an array of sensors. And you're going to give us a demo of it at some point, right? So we're going to get that set up in the lab. And so if you want to do projects that involve localization within the lab, we have a mechanism for doing that. We can put these infrared reflectors onto whatever devices, the robots, for example, and we have a system that will identify where these are in the room relative to one another. So this is this is the phase space technology. It uses a bunch of sensors. Now, by the way, these are not exactly like image sensors. In fact, as cameras go, they're rather odd. They're one-dimensional cameras. So each sensor has an array of pixels in one direction and a linear array of pixels in the other direction. Okay, that is sufficient. It doesn't have to construct an image. Okay, it just needs a single array of pixels in each dimension.
This is for tracking multiple LEDs?
Yes, this will track multiple LEDs. So this is when you run the phase space system. If you have an actor wearing a motion suit, this is what shows up on the computer screen. It shows you the position in a rendered 3D space of each of the sensors on the suit. Our system is simple because the things you have to put on your body or on the robot are passive. They're just reflectors. It actually provides its own infrared illumination, and then it just looks for the reflections. Okay. So that's what we have to say about sensors. You can have great fun in the labs and the projects with sensors. A lot of the problems you'll run into in the lab will be from not understanding your sensors. Okay? That is a very typical source of problems, and also not understanding your actuators. So it's important to put some effort into understanding how they work. All right, we're going to talk about memory architectures next. So if you remember at the beginning of the class, I talked about the way the book is organized. The book is organized to be read concurrently. You're supposed to be reading about modeling, and you're supposed to be reading about design. Right? The modeling is chapters 2 and 3 and 4. The design is chapters 7, 8, and 9. And we're now talking about design. And one of the reasons for this is that you're going to start doing really nitty-gritty design in the lab very soon. And one of the issues that you need to be able to understand to be able to work effectively in the lab in the near term is how a microcontroller with no operating system, just the bare iron, works. Okay? And I want to emphasize that one of the biggest challenges that people have in embedded systems is that they've been misled into thinking that software is what runs on a Windows operating system or an iPhone system or a Mac, right? The iPhone and Windows and Mac and Linux go to great lengths to hide from you a lot of what's going on in the hardware. And when you're doing embedded system design, you really need to understand what the hardware is doing, okay? A microprocessor is executing a bunch of instructions. What does it mean to do a context switch? How is it using memory? How is it going to behave when it runs out of memory? These kinds of things become essential in embedded system design. So we're going to start by talking about memory architectures. And the kinds of issues that come up are pretty multifaceted. One is you need to understand the types of memory you're working with. Okay? What's the difference between flash, DRAM, and SRAM? Somebody want to tell me? Yeah. Sorry? RAM is volatile. So if you well, actually, so RAM technically means random access memory, and flash memories are RAM. You can do random access on flash memories, and they're non-volatile. DRAMs are volatile. Dynamic RAMs. The way a dynamic RAM works is that it stores a bit on a charge of a capacitance, and it actually lasts only a few milliseconds. Kind of disturbing that this machine here has 4 gigabytes of memory, and if you cut power to it, within about 30 milliseconds, it will have forgotten everything. So it has to refresh every one of those 4 gigabytes every few tens of milliseconds, or it forgets everything, right? It's not only volatile, it's very volatile. It's kind of transient, right? SRAM, static RAM, is also volatile, but it doesn't have to be refreshed. So as long as you keep power to it, it won't forget. As soon as it loses power, it forgets. Okay? Flash memory will remember, even if you cut power to it. What are the trade-offs in using these memories? Why don't we just use flash memory for everything, and then we don't have to worry about volatility? Yeah. It's slower. Yeah, that's a problem. What else? Yeah, most of the technologies actually have a limited number of writes to them. On the order of, I think in today's technologies, it's on the order of 10,000. For each memory location, you can update it 10,000 times, and then it's kaput. Can't use it anymore. Okay? How do you think you design a memory like that? What happens when you hit the 10,000 limit on, suppose you've been writing a lot to a certain set of locations? Well, hopefully your memory controller will detect that and will reallocate to another set of cells. The controller becomes rather complicated then, okay? But eventually, the capacity of the memory is going to start decreasing because you don't have enough cells, right? You've exhausted them. So you don't want to be using flash to do a lot of updates. So that's another issue that you have to be aware of. In an embedded system, this is particularly critical because embedded systems are often designed to be fielded and last for, it's not uncommon to design a system to last for 5 years and have it actually run for 25 years. Okay? That's very common in embedded systems. Right? How many 25-year-old microwave ovens are there out there? A lot. And most of them still work. They weren't designed to work for 25 years, probably, but they still work. And you have to think about this, that in an embedded system design, when you're designing a laptop, it's not going to be around in 25 years, right? You just know it. But embedded systems are really pretty different. They tend to stick around much longer than you would like. Okay. Sometimes that's a real advantage. NASA has taken advantage of this, right? Some of the Voyager aircraft, spacecraft that they sent out lasted decades longer than they planned for. And they kept sending back data. Okay. And it's wonderful. Some of them didn't last past their lifetimes, and so that's life. But things can stick around for a long time. If you design a control system for a modern airplane, okay, say the Boeing 777, that was Boeing's first fly-by-wire aircraft. It started flying in 1995. How long do you think the 777 is going to be around and flying? So Boeing actually plans to make the plane for 50 years, okay? And they plan for it to fly for another 50, okay? 100 years. A friend of mine at Boeing told me that Boeing spent about $1 billion on the certification of the software for the flight control system. Okay, $1 billion just on the certification. They could actually measure how much they spent just on the certification process because they had to separate the certification process from the development process because the FAA required that. They required isolated teams. This one was doing the certification, this one was doing the design. Okay, did you have a question? This is the design of the flight control system. So this is the software and hardware that responds to the pilot controls, moving the stick and then controlling the ailerons and the rudder and the flaps and so on.
So not
Well, so an interesting thing is what got certified, right? So the software is all written in C. The FAA won't allow them to use C++ or Java. It's got to be written in C. I guess they think C is a safe language. No, they don't actually, but they at least believe that C is an understood language, okay? And it's relatively less complex. So the software is all written in C, and the focus of the certification was on the software. But it turns out that it wasn't enough to just say that the software is certified, so any correct execution of that software will safely fly the plane. No, that wasn't actually what they did. What they said was that this software is certified to run on these particular microprocessors that you have demonstrated and done all your tests on. So Boeing had to buy a 50-year supply of the microprocessors, okay, which were made around 1992. Okay, a Boeing 777 that rolls off the production line in the year 2035 will be made with vintage 1992 microprocessors. By the way, this is a problem because people aren't sure that the 1992 processors will still work. Boeing stores them in liquid nitrogen to slow down the natural diffusion processes of the dopants in the silicon. Right, because you've got impurities in the silicon. They're moving around. If they're warm, they can move. The molecules will move and diffuse through the silicon, and you have no assurance that the transistors will still be transistors in 50 years. Okay, this is a problem, right? But this is bizarre because software, right? A C program. We know what it means to correctly execute a C program. Why can't we just say that any correct execution of that C program is a correct implementation of that control system? Why can't we? Yeah.
There are no implicit timing guarantees in C.
That's right. C, when we talk about correctly executing a C program, one of the things we have said nothing about is timing. All right? A correct execution of a C program is correct no matter how long it takes to do anything. And do you think timing matters when you're controlling the rudder of an aircraft? Yeah, duh, right? So the fact is the C program actually doesn't specify the behavior that you want to certify. It specifies only some of the behavior you want to certify. The rest of that behavior ends up getting specified in the silicon and wires of the actual implementation. This is a really bad design practice, by the way, and I think that it's kind of an embarrassment to our community that we're in this situation because it means that the levels of abstraction that we're using for design have all broken down, right? The C program by itself is worthless. The only thing that is worth anything is the C program and that particular piece of silicon on which it runs. By the way, Boeing had to make sure that the microprocessors were made on the same production line. It was not okay to have them, made one subset made in Palo Alto, the other subset made in Taiwan, even if they're the same brand of microprocessor, okay? They also had to make sure they were made from the same mask set, so no bug fixes in the mask, please, okay? And they tried to buy them all in 1 week so that they were made, with the same chemical processes in the plant and so on, okay? Yeah. Quite a variety of different microcontrollers, actually. The question was, what kind of microprocessors did they use? There's quite a variety of different ones. There's a whole bunch of different software techniques that are mixed in. It's rather a bit of a hodgepodge. Yeah?
Is there a way to do this without all these problems, or is this what everybody does?
Sadly, this is what everybody does today. So there's glimmers of hope. Okay, so Airbus, I think, has been a lot more aggressive than Boeing in trying out new software technologies. And they have been using a higher level programming language called Estrel, which is a synchronous language, and it has a very nice concurrency model that is much more deterministic and much more analyzable than the one that most people use, which is threads. Estrel has actually been approved by the FAA and other similar regulation agencies for aircraft systems for use in safety-critical avionics systems. It's in fact the only high-level language besides C, which is not a high-level language, that has been approved for this use. Okay, so there's glimmers of hope, but the technology is immature. And this is, I go back to one thing that I said, in the first week. Everything you're going to learn in this class is probably going to be obsolete in 10 years, right? This is a fast-moving field, and in my opinion, most of the technology that we're working with is really quite immature, and it will change. So we want to focus on principles, okay? So focusing on principles, how do we get principles from specific examples? Well, let's look at a couple of specific examples. So here's, by the way, there's a history behind the lab infrastructure that you guys are going to be using. The first time we taught this class, we used this particular green box at the top here to control the iRobots. And this green box is made by the same company that makes the robot. And it has a very small 8-bit microcontroller in it. I like to joke that the amount of memory in this microcontroller is measured in millibytes instead of gigabytes. So it's really small, and we're kind of Spartan. And the first year, that's what we used in the lab. And it was actually a pretty darn good experience for students, because you really get very friendly with the hardware. Okay, you know what the hardware is doing when it's that Spartan. For the next 2 years, we used a higher level controller that at least was a 32-bit microprocessor, and an ARM processor, which is a fairly widely used processor in embedded systems. This is a board made by Luminary Micro, and it has an ARM processor that in the lab was being programmed, again, with no operating system. So you still get very familiar with the hardware. This year, for the first time, you guys are going to be guinea pigs, and we are together going to figure out how to use yet another hardware platform. By the way, you've heard about Moore's Law shrinking things. We keep getting bigger. The smallest one was the first one, and the Luminary was a little bigger. Now it's even bigger. I'm not quite sure why that is, but it's maybe creeping featureism. But anyway, this is the board that we're going to be using in the lab this time. And please, I ask your forbearance. We haven't used this board before. It's rather more complex than the previous ones. There is a good reason for using it. I'm going to explain the reason. But there will be glitches, and you guys are going to help us fix them and debug them. Your engineers help us solve the problems, right? That's part of the experience of working with embedded systems. It's a very interesting board because it's extremely flexible. It's got two key compute elements. It's got a Xilinx FPGA, which at least initially in the lab, we're going to pre-configure it with a 32-bit Microblaze microprocessor. So this actually takes us back somewhat to these days. This is a relatively simple microprocessor. It is a 32-bit processor, so it's not an 8-bit processor, so that makes life a little bit easier. But it's still, you're going to program it on bare iron, no operating system. Directly controlling the peripherals, directly controlling the memory. You can make a mess of things really easily. And sometimes it's great fun to do that. It's a good learning experience, okay? So that's what we're going to do initially with the FPGA, is use it as a 32-bit bare iron microprocessor. For your projects, if someone on your team has hardware design experience, has taken CS150, and you'd like to incorporate some hardware design in your project, feel free. That'd be great. You can do that with these FPGAs, okay? If you don't have someone on your team with hardware design experience, or your project doesn't justify hardware design, don't do it, okay? I don't want to see hardware designs that are capable of responding to a human's pushing a button at 1 gigahertz. Please, that's ridiculous, okay? You use hardware when software can't do the job, okay? And so think about that when you design your projects. You don't use hardware just because you know how to design hardware and you don't know how to design software. By the way, a lot of people do that, but that's a really bad reason, okay? So if you use hardware in your project, make sure that you have a reason for using hardware. All right, but it's available. The other processor on this board is a PowerPC processor, and initially in our lab, you're going to be programming this in two different ways. One is you can program it with a rather high-level interface through LabVIEW Embedded, where you construct these LabVIEW models and you run them on this processor, and you don't have any idea really what's going on under the hood, but magically your sensor data gets processed and your actuators get controlled. But for the purposes of this course, it's great to get experience with that high level, but we really want you to know what's going on under the hood. And what's going on under the hood is that LabVIEW is generating code that's running on a real-time operating system. And so we want you to get the experience of working with the code at the level of the real-time operating system as well. So the goal in the lab is to get experience with 3 levels of programming embedded systems. Writing low-level code that directly controls the hardware with no intervention from an operating system. Writing code that is mediated by an operating system, where the operating system gives you certain conveniences like being able to talk to the network. When you're running on bare iron, you could say, well, gee, can I telnet into this thing? No, you can't, not unless you write the code to handle the telnet connection, okay? But if you're running on an operating system, there might be support for that. And then the higher level is the model-based design, where you construct these models in LabVIEW and they get generated into code that will then execute on the platform, okay? And I think it's very valuable to get levels with experience with all those 3 levels. My expectation is that over time, things will be migrating up the chain and people will, in practice, be doing more with the model-based design. But understanding how it works under the hood is extremely valuable. Yeah, question?
How much is LabVIEW actually used in industry?
So the question is, how much is LabVIEW actually used in embedded industry? It's actually used a lot. It tends to be used in, I think, what the National Instruments guys called the long tail. Okay, so in particular, if you construct a plot, let me show a picture. Of say. Let's see, I'm trying to think, what are the axes that they use? The top is, I think, this is volume, so number of parts, okay, that you make and ship. And the horizontal axis is, I think, maybe dollar value, okay? So you have something like this, right? Where you have things that are relatively inexpensive, very high volume, okay? There's a lot of value in really optimizing the designs of those. They tend to be very competitive in the marketplace. You've got to get the dollar cost of your products down in order to be able to compete, and you're going to produce very, very, very high volumes, okay? You can charge much higher prices for things that are out here in the lower volume range. So very highly customized instrumentation systems, maybe you're designing an instrumentation system for the Large Hadron Collider, okay? There's not going to be 100,000 of those, okay? In fact, there's never going to be more than one. So you don't want to spend a lot of time on the optimizing of the design. So the long tail is the rather large number of projects that are out there in the low volume range. Okay, things that are done in relatively small quantities, where you want to do things relatively quickly, relatively easily. You want to be able to make them adaptable on the fly. So for those kinds of applications, LabVIEW tends to get used a lot. It's used, for example, in the Large Hadron Collider for some of the instrumentation projects that they do. So, okay. So here's what the iRobot Create command module looks like. This is the microprocessor that is on that board. It's an 8-bit Atmel processor, an Atmega 168 microcontroller. Okay, there it is in real life. Notice that the connector, this connector for the serial port, is much bigger than the sum total of all the silicon on this. Okay, this is what the architecture of this thing looks like. This is an extremely common kind of architecture to use in embedded system design. It's even in a fairly sophisticated system. Often you will have several of these 8-bit microcontrollers and maybe one big controller running a Linux or an embedded Linux or something like that. Okay, so embedded system designers use 8-bit microcontrollers all the time for a lot of different applications. It's not just for microwave ovens. Okay. So here is what the architecture looks like. This particular processor that we were using had a flash program memory with approximately 16K bytes, okay, 16 kilobytes, okay. That's your persistent memory. How much persistent memory do you think is on this laptop? Sorry? Yeah, the hard drive space is persistent memory. So, yeah, I think it's about 120 gig. So 120 gig versus 16K, pretty different, right? You're not going to run PowerPoint on this processor. Okay, you can't even get the fonts from PowerPoint onto the memory. In fact, you can't even get one of the fonts on there. Okay. It's interesting to try to restructure your thinking to what you can do with very small amounts of memory. The random access memory is 1 kilobyte, okay, versus 4 gigabytes on this thing. That's a big difference. And the way that the data memory is organized is shown down here. There's a logical address space, okay, which is shown using hexadecimal numbers here for the addresses. By the way, as an embedded system designer, you've really got to get used to plowing through 400-page spec sheets with lots and lots of diagrams like this, okay? And in fact, you're going to face this in the lab. The documentation for the board that you're going to be using includes, I don't know, a 250-page document that explains the microblaze architecture, another huge document that explains the Xilinx FPGA, another document that gives you the PowerPC architecture, another document that gives you the VxWorks operating system specification, another document that gives you the LabVIEW interface. It's, overall several thousand pages. You don't want to just, sort of sit down one evening and start on page 1 and start reading. That doesn't work, right? You have to learn to find your way through this massive stuff to zero in on the information you need. That's reality. That's the way it works in the real world. And it's good experience to try to figure that out. Now, the lab TAs, have been through quite a bit of that documentation, so they'll try to help guide you. And we have these lab write-ups that'll give you some pointers that'll save you an enormous amount of time finding what you need to know. But don't hesitate to go to the source documents. It's actually pretty easy, especially, if they're PDF files. If they're paper, it's a real pain because it's sometimes really hard to find stuff. But in PDF, you can just search for it or Google it. So anyway, so here is a map of the data layout. And it shows that the addresses are 16-bit numbers. This is an 8-bit microprocessor with 16-bit addresses. What does that mean to be an 8-bit microprocessor with 16-bit addresses? Yeah.
The add output is like 8-bit, but then it like we have memory of like 2 to the power of 16. Like,
Yeah, so what is 2 to the power 16?
how many locations the address?
No, I mean, what number is it? It's about 64 kilobytes, right? And but there's only 16 kilobytes. Actually, no, sorry, this is the data memory. There's only 1 kilobyte. Okay. What's the discrepancy there? Why? I mean, the 16-bit addresses, but I've only got 1 kilobyte of memory. Yeah.
There are memory maps, so the other stuff are memory maps and other locations.
Yeah, so the key thing here is that you've got to understand how memory addresses get mapped into physical devices in memory. If you're programming at the bare iron level, you have to understand that. You can't get away with ignoring how memory addresses work. And that's the key, one of the key properties of actually, controlling the hardware is understanding what a memory address means on this particular implementation of the hardware. Now, the fact that the addresses are 16 bits means that you could have used the same microprocessor and put more memory on the device. But this particular piece of hardware didn't put more memory on it. Consequently, there are holes in this memory space where there are addresses that don't correspond to any memory. Can you write a C program that will write to those addresses? Absolutely. Can you write a C program that will read from those addresses? Yeah. What are you going to get? I don't know. Maybe zeros, maybe garbage, maybe it'll wrap around and read some other address in memory. All of those are possibilities, right? If you use a memory address that does not correspond to a physical location, the hardware will do something. The C program will execute. It'll give you a result of the read, and what you get will depend on the hardware implementation. Okay? That's one of the things that makes debugging C programs on these processors really fun. Okay? If you have an error in your C program and you start reading from memory that doesn't correspond to physical addresses, all kinds of interesting things can happen that will make you scratch your head and you won't be able to see what's going on. Because there's no printf statements on this. Okay? Where would a printf go? Yeah. You could write code that would talk to the serial port, and you could connect up a terminal to that serial port that would read the data. Okay? But what if that code doesn't work? Actually, the code that writes to the serial port is actually pretty non-trivial. One of the project teams in that first year needed a second serial port so that they could have a Bluetooth connection along with the serial port connection. And they made a serial port out of a GPIO pin, which is a pin that you can, from the software, you just tell it to be either high or low. Okay? And they wrote the code to turn that into a serial port. It took them an enormous amount of effort to do that. Very painful. Most of the students who were debugging were actually lighting these LEDs instead of doing printfs, right? So that they would light the LED when their program got to a certain point. And then they could tell the program had gotten to that point. Okay? Sorry? And playing audio tunes, that's right. So this device has a little piezoelectric speaker on it, right? The way that works is you make sounds by turning on and off a voltage at a certain frequency, and you can make it buzz, you can make it play certain tunes. If you get the frequencies right, it'll sort of sound like, a musical sound, sort of. Not a particularly pretty one, but yeah. All right, so this is about understanding the hardware. So the memory map is a big part of the hardware. So this is the particular memory map here, and you can see the way to read this is that the lowest 32 bits, sorry, the lowest 32-bit at the, I'm having trouble speaking, sorry. The lowest 32 addresses don't refer to memory at all. They refer to the registers of the processor, okay? This includes the program counter, by the way. So what happens if you accidentally overwrite the program counter by writing to the memory address that contains the program, that refers to the program counter? Well, you'll start executing whatever is in memory at the address that you just put into the program counter, whether it's a program or not. Okay? That makes debugging fun. The next 64-bit, 64 addresses refer to I/O registers. By the way, how big are each of these registers? How many bits? 8. It's an 8-bit processor. That's what it means. All the data is 8 bits. Data is referred to in 8-bit chunks. The fact that we have 16-bit addresses is pretty convenient, because if we only had 8-bit addresses, we would only be able to address 256 bytes of memory, right? Okay, so we have 64 I/O registers. What happens if you overwrite those by accident? You change your outputs. So your robot could start doing crazy stuff, okay? The next 160 are also I/O, but those happen to be, I think what it means by external here is that there's no hardware provided on this device for them, but you could hook up hardware to it. And then the remainder is the internal SRAM, and that ranges from this address, which is a hex 100, up to some number that is basically 1 kilobyte bigger than that. Now, how is that data RAM used? Well, in C programs use a stack. The compiler generates code that every time you call a procedure, it puts stuff on the stack, okay? What does that mean? Well, it actually starts using memory from the bottom of the memory like that, okay? So when you call a procedure, the address from which you called it gets stored into memory at the location of the stack pointer, okay? Then the current register values, 32 of them, up to 32 of them, also get pushed onto the stack, okay? Then you update the program counter and start executing a new program. At that point, you may also put local variables on the stack, okay? Meanwhile, your stack pointer keeps going up, okay? And each time you do a procedure call, your stack pointer goes up, which is actually down in addresses, right? What happens if you do too many procedure calls? Your stack pointer will start writing to these external I/O devices, which aren't provided, by the way, so what happens when it reads those values back? So if you call a procedure and your stack pointer is already in here, you push your return address onto the stack. Your program will happily write to an external I/O register the return address. When it comes back to that, if it ever comes back to that, which it probably won't, it will get the return address from this external I/O register, which doesn't exist, and start executing code at this address that who knows what it is, right? You get chaos very quickly, okay? So you have to pay attention to what's going on in the processor in this case. You've got to pay attention to the depth of your stack. All right. So let's look at the C programs and understand how they work. So in the lab, we're going to be programming in C, not because I'm enamored of C, but because it has a really big advantage that, unlike Java, it actually does allow you to mess up in very interesting ways. You can directly control the hardware, okay? And in Java, deliberately makes that hard to do because they don't want you to mess up the hardware, okay? But here, we do want to be able to mess up the hardware because we want to be able to do creative things with the hardware. So So we got to understand how C interacts with the hardware. Okay, so what is meant by the C code that's shown here? Someone want to tell me what these 2 lines of C mean? Yeah, for this processor.
First line finds that X is a pointer.
Okay, so how much memory is used by that line? Yeah.
Is it just pointing to the I/O register? What are the I/O registers? So it's 8 character. So it's a pointer to that I/O register, which is in the command.
Okay, that's a good point. So the first line is declaring a variable that's a pointer, okay, and the second line is assigning it a value. And the value that is assigning it is, in fact, the first of the 64 I/O registers in this processor. That's correct. How big is the address, however? It's 16 bits. It's 2 bytes, right? So we've used up 2 bytes, okay? Only 2 bytes, right? The value pointed to by X, is that in memory? No, it's in one of the I/O registers, right? So we didn't actually, these 2 lines of code used up 2 bytes of RAM. Where in RAM? Maybe, wherever the stack pointer was. It kind of depends actually on where this code is. Okay, so we need more context. We need to know the rest of the C program to know where in memory this is. Yeah. Yes, 16-bit address, 8-bit processor.
And so the pointer itself is 8 bits.
No, the pointer is 16 bits because the pointer is an address.
Okay.
Right. So the fact that it's misleading, it's confusing, right? Because it looks like, well, gee, I only specified 8 bits. Right? But the compiler knows that this is a 16-bit number, and it will automatically reinterpret the 8 bits that I specified as 16 bits and 0-pad them. That's what the compiler will do. Okay? Yeah.
Wouldn't this be written into the memory assembly format?
Yes, but I've told you enough about the processor to know what it's going to look like. I mean, this is a compiler will translate this into a very simple, probably single line of assembly code, okay, which is essentially something like a move immediate of this constant 0x20 into whatever location it decides, but we need to know what location this is. So odds are it's going to be, you know, something pointed to by a register, Rn. Okay. So this will be translated into some assembly language instruction like that. Okay, but we need to know more context to know exactly how it gets the address into which it writes this pointer. Okay, let's look at a slight variant of that. Suppose we have this one. What's going on in this code? By the way, can I have a show of hands that you're comfortable enough with C that even though I'm trying to be tricky, these are questions that make sense? Okay, if the questions don't make sense, please go find a book on C and read it, because you're going to have trouble in the lab otherwise, right? Even if the answers are not coming to you immediately, if the questions make sense, you're in good shape. Okay. So, all right, what does this code mean here? Yeah.
You're reading the value? I mean, you set up X the same way, pointing towards the first.
Right. So this is going to store into Y the value read from the first of these 64 I/O registers. That's, by the way, that might be telling you something about what the physical world is doing. You might have an external device that is controlling the value of that register, and you're reading it now, and now you've got it in your program. You know what the physical world is doing. You can do a branch on that. How much memory have I used up with this code? "24 bits? Nope. Oh, yeah, sorry. Apologies. Yeah, 24 bits, 3 bytes. I did the arithmetic wrong in my head. 3 bytes, right? Because y is going to take 1 byte. Star x is going to take 2. Yeah. Yes, you're right. The instructions take up more memory. But an interesting thing is that the instructions are not stored here. They're stored in flash. Okay? And we have 16 kilobytes of flash. Okay, here we have more context in the C program. So suppose I have a C program that looks like this. I've declared a procedure called foo that returns a char, which is an 8-bit quantity. It declares local variables. X is a pointer, Y is not a pointer, and has a little snippet of code where it puts into Y the value of this external register and then returns that value. This is, by the way, a nice abstraction mechanism. I would like to know what my accelerometer is telling me. I could write a procedure that says accelerometer data, okay? And then I just call that, and I don't have to remember what memory register it's at and so on, okay? So this is going to return whatever is in that I/O register. Now I have at the top level of my program, I declare a char z, and then I have my main program that simply calls foo. So the question is, where are x, y, and z in memory here? Yeah. In the stack? 2 of them are on the stack. Yeah. Z is in the globals, right? And it's kind of up to the compiler what to do, but a pretty typical thing to do for a compiler to do is to put the globals at one end of the internal memory. So it'll start at this address, okay? Allocate memory for your globals, okay? Your static variables is what they're called in C. And the reason it allocates them here is that because this variable z is declared outside of any procedure declaration, it is live for the entire lifetime of the program. That's why it's called a static variable. You need a memory location for the entire lifetime of your program to store that variable. So, yeah. It doesn't get, that's actually a really good question. The question was, why don't we put it in the program memory? Someone want to field that one? Yeah. It couldn't be written to if the program memory can't be written to, but this is a flash, so we can write to it. Yeah. The program memory is slower, but it also has a limited number of writes. Okay? So probably a decent compiler wouldn't, by default, without you going to some lengths, right? You probably would have to force it to use the program memory. How would you force it to use the program memory? Suppose I really want Z to be in the program memory. Yeah. Yeah, you'd have to specify the address. You'd have to know where in your address space the program memory is. And then you have to make sure that the compiler doesn't, use that address that you just used for your variable in some other way, okay? So it could be kind of tricky to force this thing to go into program memory. By default, it's almost certainly going to go into your data memory. By the way, it's very common for these kinds of architectures to be used not with flash, but with ROMs, read-only memories for the program, right? If you put this, you could use this as a development system for your microwave oven. But you don't want to ship your microwave oven with flash because flash is more expensive, right? You can pair off a few costs, and plus flash can, you don't want your users overwriting the program, right? So you burn it into ROM, and then it's a read-only memory. It can't be written to at all. And now your program memory space can't be updated at all. So, okay, so the key thing here is that X and Y go on the stack. We've used up 3 bytes of stack space for those. We've used up 1 byte of static memory. If the static memory is put at one end of the address space and the stack is put at the other, what kind of interesting program bugs are you going to get when your stack overflows into your static space? Well, you know, the value of the variable z could suddenly randomly change to some weird number that you have no idea where it came from, the return address for a procedure, for example. Okay? Nasty bugs arise like that. Okay, we'll spend a little more time on Thursday looking at memory models, and then we'll delve into I/O in a little bit more depth next time.